Hello everyone. For the next few weeks until April 12th, looks like we'll be doing online lectures. It seems that the labs will still run as normal, but please watch for announcements for the most up-to-date information regarding that. Today we'll be looking at Chapter 23 on circuits. We'll explore some simple circuits and the diagram symbols that go along with these. We'll explore series versus parallel circuits, and then finally we'll look at what it would be like to analyze a full circuit. In other words, to perform full circuit analysis. Our next homework will be due on Wednesday, March 25th, and the info in this and the next few lectures will help to prepare you for answering those questions successfully. So let's continue. So chapter 23, our goals are to be able to properly represent circuits using circuit diagram symbols. That's what we'll do first. Then we're going to work with two laws called the Kirchhoff junction rule and the Kirchhoff loop rule to analyze circuits. We'll also take a look at resistors in parallel and in series, and we'll be able to reduce a bunch of these resistors, a so-called network, into their equivalent resistances. Finally, we'd like to be able to analyze some simple RC circuits. This means a resistor with a capacitor. So you've already seen something like a light bulb connected to a battery before in our previous discussions. And when you think about circuits, maybe what comes to mind is a picture like one of these two, that you think about a computer circuit with lots of little wires, or maybe even wires etched onto a circuit board that is set to perform some kind of task. So here's a question, and I guess I'll just make a general comment here, is that it is sort of tempting. Let me make sure it's really recorded. Okay, it's recording. That's strange. Okay, so we are recording, but I'll just make a general comment that it's tempting to kind of get passive about this and just kind of listen to my sweet voice. I don't know, maybe it's annoying, but anyway, this is my voice. Listening to some narration around all this here and thinking, okay, yeah, I got it, that makes sense, okay, good. But the point is, I want to challenge you to take an active approach towards your learning, which will involve really sitting down with a pen and paper and trying to really work things out. And so it may be that a good strategy is to have a friend to be sitting with and saying, all right, let's pause it here. Let's see if we can get this one. Okay, so you'll hear me say pause sometimes, and I will give a moment, then just let you pause it, and then when you come back, then we'll take a look at questions like this. So in this case, please pause and try to sketch the circuit diagram for this picture that's shown at the top here, and then we'll discuss which of the following circuit diagrams is the best representation of this above circuit. Okay, so we're back. We'll return to this one in just a second, but taking a look at the different kinds of circuit elements here, we'll see that we can actually show a battery this way, whereas a wire is just a straight line. A resistor is kind of the zigzag thing, and sometimes you'll see that we'll draw a light bulb as a resistor, or there's even its own symbol for a light bulb that you might sometimes see. And a capacitor is written as two parallel lines to sort of symbolize the two parallel plates next to each other. So a resistor and a capacitor connected to a battery here could be drawn like this. So how about the one that we looked at from just before? Well, in this case, the best representation would actually be case A. Now I'm going to move to the sketch to show my representation. Now you'll see that I've actually already drawn a lot of these things. It's because I had just recorded this entire lecture and then realized that somehow the recording was not working, so I'm doing it again. And I'm just going to use the drawings that I've made so far. So here's the sort of rough sketch, my picture, and to make it into something that looks a little bit easier, I've used the corresponding symbols. And so the symbols here are a battery, a resistor, and two capacitors. Notice that that is going to be the same as something like this here. Notice that simply just sliding them around doesn't really make any difference. So that's the point about this part here. And we'll go back to the slides. Okay. So in this case here, we have a light bulb that has a resistance of 1 ohm. So we could actually draw it as a resistor if you wanted to. And so we're going to be talking about a voltage difference between 2 points. So like, so let's say you pick any 2 points along this circuit here, points A and B, and then delta VAB is going to represent the magnitude of the potential difference between points A and B. So for example, if I wanted to know the difference in voltage between point 1 and 2 here, I could say delta V12. Or if I wanted to know the difference between 4 and 1 here, I could say delta V41. So delta V41 would actually be 3 volts because that is the voltage across the battery. So what are the values of delta V12, delta V23, and delta V34? I'll give you a moment to figure that out. Please pause and take a moment. So I will switch to the pen and paper here. Okay, 2 and 1. Okay, so this is going to be a 2 and a 1. And this is a 3 volts here. And we can take a look at this kind of circuit here. And we could say we can apply Kirchhoff's voltage loop rule, which says that I can pick a direction for the current. Let's just say that the current is going up this way. And it's the same current, it turns out, that's going to be going all the way through this circuit here. And if I started here, let's say, then going across this 3-volt battery is going to give me plus 3 volts. Going across the resistor in the direction of the current is going to give me a minus I times R of the 2 ohm resistor. And going across this resistor here is going to give me a minus I times R of the 1 ohm resistor. When I finished, it's actually going to, in an ideal wire case, it's going to take me back to where I started. So in other words, that sums up to 0. That's the Kirchhoff's voltage loop rule. So notice here that I times R2, well, that's just 2 ohms. And this is just 1 ohm. So I can write 3 minus 2I minus I is equal to 0. Or I can rearrange that as being 3 is equal to 3I, or I is equal to 1 amp. So notice that you don't have to worry too much about how the units work out, because as long as you're using amps and ohms and volts, then everything is going to work out such that current times the resistance is always equal to a voltage. So let's go ahead and compute then some voltage differences then. So if the current that's going through this 2 ohm resistor, I, is equal to 1 amp, then we could say, well, what's the voltage difference between this point and this point right here? And that's going to be delta V, and I guess in the language of the question that was asked, that was asking between points 1 and 2. And notice how I'm not being so specific on whether it's here or here, because I know that this place over here and this place over here has the same voltage. So delta V between points 1 and 2 is actually going to be equal to I times R. So that's going to be equal to 1 amp multiplied by 2 ohms. And so if I multiply it amps times an ohm, that's going to get me volts. So that'll be 2 volts. Similarly, if I wanted to find the voltage drop across this place here, delta V between points 2 and 3, I can say that that's also 1 amp multiplied by 1 ohm. So in other words, that is 1 volt. Finally, we can take a look at between this point here and this point here, and as we discussed, in an ideal wire, there is no voltage drop across the wire just because it has a very low resistance. So in other words, you could say, well, the voltage drop from here to here actually is, between this is points 3 and 4, is equal to 1 amp times the resistance of the wire. And that's actually true, but the resistance of the wire is very, very small, so small that we're going to consider it to be almost zero. So we can say that the difference in voltage between these 2 points is basically zero. Second part says, well, what would the values be if the bulb is removed? So there's 2 ways of meaning the bulb is removed. One looks like this, where the circuit is now broken and there's no current flowing through, in which case everything along this side is going to be at 3 volts, and everything on this bottom side here is going to be at 0 volts. So the difference between, say, points 1 and 3, or points 2 and 3 is going to be 3 volts, and between 1 and 2, and also between 4 and 3, is going to be 0 volts difference. Another way to look at it or interpret this problem is to say, well, what they mean maybe is just if it was a wire instead of the bulb being there. So in that case, we could take a look at the, what if it was just a wire? And we'd get something that looks like this. We'd have our 3-volt battery, we'd have a 2 ohm resistor, and the voltage difference between points 1 and 2 would then be a different amount of current, which is now calculated by also using the Kirchhoff's voltage loop rule, which says 3 volts minus I times R is equal to 0. Solving for I, we get 1.5 amps. So putting in that 1.5 amps in here, we actually see that the voltage drop now between the 2 points is actually 3 volts, which is the same as the voltage drop across the entire battery. Now let's take a look at Kirchhoff's laws for the conservation of charge and the conservation of energy. So in the case of conservation of charge, imagine that you had some cars that were going down a little highway here, and some of them split right and some of them split left. And so let's say you had 100 cars that went in, and you counted that 60 of them went to the right. Well, that must mean that 40 of them went straight, given that none of them went actually backwards. So that statement, as far as current or the flow of charges goes, it says that I1, in this case the current that goes into the junction, is equal to I2 plus I3. That's what these little sums mean. They're the Greek letter S, which means a sum, meaning adding up everything that goes into a junction and then everything that goes out of a junction, and that those two should be equal to each other. So Kirchhoff's loop law, which is what we actually just applied to this last problem, that basically says that if we go around a loop, a closed circuit, and we start, let's say here, then we'll have a voltage, either a gain or a drop across each element, this element, the second, the third, and the fourth. And then by the time that we got back to where we started, that all those voltage gains and drops should add up to 0. And that's a statement of the conservation of energy, actually. So it's kind of deep thinking, but this is kind of the law that we use, and we'll put this into use right away. So a full analysis of any circuit is going to mean measuring the potential difference across each circuit element and the current that's going through each circuit element. Here are some general strategies for how to solve a problem. A couple of things that I'd like to point out is that when you're going in the direction across the battery terminal from a minus to plus, this is usually written as a voltage gain. Whereas when you're going in the flow of current across a resistor, we know that there's going to be a voltage drop. Think of it like if you're walking along a river and this river is flowing downhill. That means that you're slowly walking downhill. And so your potential, your gravitational potential, is decreasing. So if you're going in the flow of current, then you're getting a dropping of potential. Okay, so now you know how to solve a problem like this. Now let's take a look at resistors that are in series and then in parallel. So in this case here, we have resistors that are in series with each other. Maybe you know from watching Netflix that you've watched a TV show, and then you watched it all the way through, and then you finished that one, and then you picked right up on the next one, and then watched that next one all the way through, and then picked up on the next one, and so on. And so this is called a TV series, because maybe you found yourself at 2 in the morning wondering where all the time had went. In this case, you have two resistors that are in series with each other, and the idea is that when we go into one, then as soon as we go out of the next one, then we're going into the next one. And so this is the meaning of how you can tell if something is in series with each other, is that there's no other way to go except to go through the next element. That means in series. If two resistors are in series with each other, you just add them up directly. So for example, if resistance is 10 ohms and this one is 5 ohms, then together they make 15 ohms. If you have a bunch of them that are in series with each other, you just add them all up directly together. So that's pretty straightforward. Another thing to notice is that the current that goes through these resistors is going to be the same in every case. That's because there's no junctions. There's nowhere for it to go if you have resistors that are in series with each other. So the current that goes through one resistor is going to be the same current that goes through the other resistor. In contrast, parallel resistors are going to have a junction. And so they add in a weird way with each other, which we'll practice in a moment here. But one thing to notice is that the voltage drop across each of these resistors that are in parallel with each other is actually the same. So it's the same voltage drop across any resistors that are in parallel with each other. And so what we do is we add up 1 over the first resistance, 1 over the second resistance, and so on. And then notice this, that we're going to actually take it to the -1 power. In other words, we're going to take all this stuff and go 1 over, and that'll give me my equivalent resistance, the EQ, or the total resistance. So I'd like you to pause here for a moment and see if you can calculate the equivalent resistance for each of these two groups of resistors. One of them is resistors in series. The other one is resistors in parallel. Okay, so let's go ahead and cut to the camera. I'm going to take a piece of paper here, kind of simplify things just a little bit. Okay, now I will show you my thinking. The three resistors that are in series with each other can be written as one resistor with 11 ohms. The way I got this was by saying that the total resistance, or equivalent, sometimes I write RT for T is meaning total, or REQ, where EQ means equivalent, just to let you know my notation. And I literally just add them up directly. Not so bad. 2 plus 3 plus 6 gives me 11. So that group of three resistors is actually the same thing as one 11 ohm resistor. When we have the 9 and the 3 and the 6, they don't add quite so simple, but they can still be reduced to a single resistor. I got a resistance of 1.6 ohms. And the way that I got that was by adding 1 over R1 plus 1 over R2 plus 1 over R3. And then you might think, okay, I've added them all up together and I got 0.611. And it's tempting at that point to say, okay, then that's my answer. Oops. But please be careful that you finally then take 1 over that number. So in other words, I need to do to the -1 for both of these, or in other words, 1 over this number to get the total resistance. Okay, so that gives me my total resistance is 1.6 ohms. And so one of the things I want you to note here is that, did you notice that the ones that we dealt with in this series were lower resistance values, 2, 3, and 6, compared with the parallel case, which was 9, 3, and 6, and yet the overall resistance was actually lower. So one thing that I want you to notice is that when you add more resistors in parallel, that actually decreases the overall resistance. It's a little counterintuitive. More resistors, less resistance? But what you're doing is you're giving the flow of electricity more places to go. So you're giving it different pathways that it can flow. And so by putting putting these resistors here, you're actually giving more pathways, and so overall the resistance goes down. So even if I were to put a 100 ohm resistor here and like a 10 ohm resistor here, then this resistance would still go down compared with if you just had the 3, 6, and 9. So yeah, pretty strange, maybe a little counterintuitive result, but that's the way that series and parallel resistors work. Okay, I think that I will pause there. That concludes our lecture for lecture number 14, and we're going to carry on with the next lecture talking about more complex resistor networks, capacitors, and then finally resistors with capacitors. Thank you for watching.